Okay, so let's continue with locally linear embedding, and which is a series of lectures on this specific topic. And LLE, as we discussed before, is one of the very first nonlinear dimension reduction algorithms. And we have discussed in the previous 2-3 lectures about its theoretical properties. And today we will continue with it. And this time we will discuss more about this paper, Local Linear Embedding Hits Boundary. That is, when a manifold has boundary, then how does local linear embedding behave? And what is it? How much do we know about it? Spoiler alert, we know very little. And there are many open problems when a manifold has boundary, and we seriously don't know. We still have a lot to do. So this is the model. But this time, the only difference with the previous lectures will be now we have boundary. Okay, and all the others are the same. You have a manifold, smooth, compact, and so on, induced matrix. You have a high-dimensional vector with support on the manifold. The density function, induced major is absolutely continuous. You have sufficiently smooth density function, and so on. And when we analyze the boundary, actually the density function regularity can be reduced, but we still put C5 here. And then, just like before, almost the same, we sample endpoints IID from the random vector, and if you have a function on the manifold, we do the discretization. Okay, so topics 3. So we want to discuss boundary. And here is a keyword, Dirichlet. And what may remind you, when we discussed diffusion maps, asymptotic analysis, when there is a boundary on the manifold, then we have the Neumann boundary condition. And here, it seems that seems to suggest that we may have Dirichlet boundary or something. Well, we will see. It is related, but not quite so. So first, what is boundary? Let's say this is a manifold, and the boundary is smooth. That is our assumption. But if you pay attention, you will see that the true boundary is of major 0. Major 0. So you cannot actually sample it, okay, if the density Q is continuous. So the only thing actually we can consider is a ring, or M epsilon, which is a ring near the boundary, which I put as the orange color. This is a ring, okay, and this is an epsilon distance, which is every point inside this orange ring. It will have geodesic distance to the boundary less than epsilon. So this is a ring. And if you subtract this ring, this is we call interior or far away from boundary. So the definition is slightly different when we discuss boundary and interior when we discuss differential geometry. And the main reason is because we cannot really sample the boundary. And this we have specific information. For example, you really know where the boundary is. You sample points on the boundary, but then will be a different set. Okay, and this problem is related to the boundary detection problem, but well, it's a different problem, and it's actually quite challenging. And there are some new algorithms and so some results. Some are based on this local linear embedding, but we will not discuss it today. So recall the LLE kernel in the manifold setup. So that is what we have seen before several times. You have LLE kernel, which is 1 minus this guy. This is 0, 1 kernel. This is about curvature, and the TXT. This covariance. This is augmented matrix. It has some good property. It has some good format. And this is lambda I plus C. This is the interaction in between the normal direction and the regularization. Okay, so that is everything we have known so far. And where Cx, this Cx, Cx is a local covariance matrix, and it is inside Tx, which I don't really show here. But if you go back to the previous lecture, you will see this is a local covariance matrix in a continuous format. C, this is outer product, this is density function, and then you have the asymptotic expansion. Okay, and in the last lecture, we know the behavior of the eigenvectors and eigenvalues and how it is perturbed from the ground truth tangent space and normal direction and so on. And also recall the main theory. What we had before was if you choose rho to be 3, and what is this rho? Just give you a quick hint, quick recall. We have C, which is epsilon d plus rho. Okay, this is how we choose. Rho is in R. Okay, this is how we choose. And epsilon is the bandwidth, if you remember. Epsilon is the bandwidth. And the C is the regularizer in the when we evaluate barycentric coordinates in the LLE algorithm. Okay, and what it says is if rho you choose to be 3, rho choose to be 3, and epsilon and n are chosen in the following are chosen and they fulfill some relationship. That is when n goes to infinite, this quantity goes to 0, which says locally you have sufficient points, and epsilon goes to 0. Then with high probability, this is 1 minus n raised to minus half. So not half, 2 minus 2. Then what you get is Laplace Beltrami operator. And remember this omega I, this is a barycentric coordinate, and this product will give you f of xi, this is xi, and Laplace Beltrami operator at xi, and have some arrow terms. So this is what we have seen last time, and you can see some good properties. For example, non-normalization, convergence rate, and so on. This is just a recall. So because of this result, we will focus on the kernel with rho is 3. That was what we will focus on. And remember, recall this plot. You have boundary, you have the boundary rho, and so on. And we have some quantities that we define here, and we will just they are just a constant that we'll encounter when we do the calculation. Okay, and in this case, what do you get? You will see that the kernel k epsilon will be 1 minus order of epsilon. Okay, and this is something good you can expect. Almost like constant. And but near the boundary, it will be different. It will give you something, some more correction. And this correction UD is a normal direction. Okay, and the sigma 1D is here, sigma 2D is here. And what is epsilon tilde x? That will be the geodesic distance of x to the boundary. This is the geodesic distance. So you can see you have xy at x, okay, and x is inside the ring. Then the kernel near the boundary will have some extra correction here. Okay, but if you are away from the boundary, which is in the interior part, then the kernel is actually good. So they are related by this extra term. Okay, so that is what we have. Now if we pay careful attention here, you may see that, well, this guy may give you something crazy, isn't it? Because you have some kind of 1 over epsilon. So maybe you will see something totally wrong or totally error or whatever. We don't know. Then what can we say about it? Actually, the theory tells you that, well, this may be negative, but it doesn't go crazy. Actually, what you can show is the expectation of the kernel associated for fixed x associated with y. This is expectation of x. Actually, this is a positive constant value. It's always positive, of order epsilon d, but always positive. no matter where you are for any x. Okay, and there will be some constant c constant depending only on d and the p and so on. So that is the summary. So although the kernel may have some fluctuation, maybe near the boundary, but the expectation is always positive. That is, it doesn't really go crazy. So this is a visualization. Look, when you have a kernel near the boundary, you can see that you have positive on the boundary side, but negative value away from the boundary side. Why so? Because near the boundary, okay, if you find neighbors near the boundary x, if you find neighbors and you want to determine the barycentric coordinate, then the barycentric coordinate has to have positive or negative. Otherwise, it cannot really represent x. But if it is really away from the boundary, then you have all the neighbors that are kind of evenly distributed in all directions. So when you evaluate the barycentric coordinate, it will be always positive. That is how it looks like. So this is a relationship. So near the boundary, you will see that in this picture, near the boundary, this is positive, and this is negative, which gives you a balance. That is how it looks like. But if you go to this point, which is away from the boundary, like this, away from the boundary, right? Then you see everything is positive, like constant. And on the right-hand side, I just show you the expectation of kernel LLE for every point x by the expectation of capital X. So you see everything is positive everywhere, numerical. So that is a numerical visualization of the LLE kernel, which tells you that near the boundary, okay, even if you choose C, the regularization, correctly, sorry, near the boundary, it is no longer a diffusion process. It is no longer a random walk, because the barycentric coordinate is no longer positive, so you no longer have a random walk behavior. So here is the main theorem. The main theorem tells you that, look, as I told you, when rho is 3 and you do not have boundary, then you can recover Laplace-Beltrami operator. But if now we have boundary, what will we get? Here you see, so F is C3, P is C2. Okay, we don't need the high regularity, because right now we have fixed rho to be 3, so rho can be only C2. And suppose we have epsilon, so that all these are satisfied when n goes to infinite. Then we have with probability greater than 1 minus n raised to minus 2, such that the the LLE matrix minus I, F, and J summation, this guy will approximate a differential operator d epsilon, f epsilon square, and higher order errors. Okay, and the implied constants behavior is written here. What is interesting? The interesting thing is this d epsilon. D epsilon is a second order differential operator, but it has very peculiar behavior. As we will see in a bit about what phi1 and phi2 are, what you see is you have I from 1 to d minus 1 partial II squared, and this is partial dd2. What is II and the dd? We choose the coordinate so that the d's coordinate pointing to the outer normal. And for the other d minus 1, they are tangential to the boundary. That is how we choose the coordinate and write down the differential operator. And in this coordinate, you can see that you have the d's coordinate that have some separate written term. And as we will see in a bit, this guy is actually a mixed type. It has elliptic, degenerate, and hyperbolic behavior. Why? We will see this phi1 will always be positive, but phi2 will go from positive in the interior to negative near the boundary, and it's continuous. So it will cross 0. And you have also first order term in the normal direction. So what is this guy? Let's take a careful look. This is how the picture looks like. You have rho 1, which is always positive, and phi 1 is always positive, and the phi 1 is this constant inside in the interior, far away from the boundary. But for phi 2, it will be negative on the boundary, and 1/2 times d plus 2 away from the boundary, and then there will exist, okay, a d-dimensional one subset, which is has phi 2 0. So if you pay attention to this negative, positive, 0, and the phi 2 is continuous, that explains why this guy is elliptic. This guy is elliptic, far away from the boundary, but hyperbolic near the boundary. And it is degenerate because this guy is gone, becomes 0 over this red dash one-dimensional subset. So this is the pointwise convergence tells us. We will get something very, very strange. What is it? At this moment, we still don't know. We only have pointwise convergence. And how to analyze this operator? Well, some of my collaborators are working on this with his students, but so far we don't know too much. And this is a one-dimensional case. Okay, I just showcased to you. You can go to the paper and see more details. It just tells you that if we work with a one-dimensional manifold, which is very, very simple, then actually you can precisely write down the d epsilon operator, which has this beautiful, beautiful behavior. You can see the a second order derivative, okay, is positive inside, negative near the boundary, and you have first order differential operator, which is 0 in the away from the boundary, and the positive near the boundary. And even this one-dimensional thing is not very easy to analyze, and not much is not. Okay, and this is the behavior. If you run LLE on the 0-1 interval and plot all the eigenfunctions, you can see the eigenfunctions will have constant, linear, and some kind of maybe sign. You see this guy is like Dirichlet, but you start to get something, well, it's just hard to say what's going on. We have no idea. It's not very stable near the boundary and so on. And even you can consider disk. If you have a two-dimensional disk, which is flat, with boundary, which is S1. Very, very simple example. In this case, you can see this is what I plot here. The color is the value of the function, so I only plot the eigenfunctions. Okay, the eigenfunction value is colored here to show you, to visualize the eigenfunctions. You can see this is like linear, right? And what is this? Well, but this one, hey, this one, they look very much like the eigenfunctions of the Laplace-Beltrami operator with the Dirichlet boundary on a disk, right? But what are they? What are they? This seems to be kind of interaction of the eigenfunctions on the boundary. Look, this is like if you just focus on the boundary, this looks like a sine, right? This looks kind of cosine, and this one as well. That seems to have some, and this seems to be sine cos 2 pi, 2 whatever. This is sine 2 theta, and this is sine theta, and so on. So it seems to have some kind of interference in between the boundary eigenfunctions and the interior boundary functions and so on. Everything is mixed up together. So we do not know too much. And back in 2019, 2020, we just say, how about the following? Suppose we know the boundary. Suppose we can detect the boundary. Then we know that there is a wave region, right? This region outside the dashed red. It is kind of a wave equation, hyperbolic. right? So how about if we just remove every point inside after we calculate the LLE matrix? We just say, okay, after calculated LLE matrix, suppose we know these entries, those points are on the wave region, then we just remove the rows and the columns and get the remaining part that we called the modified LLE matrix or clipped LLE matrix. What you can see here is BB, this is the boundary, really the boundary, but this boundary is away from the true boundary. This is the rim, sorry, this is the rim part away from the boundary, and there's a transition part. There's a transition part here, okay, and there's also interior part. So this white part is the interior part, this pink part is the transition, and this one, this part, which is inside, this is original, in the original side, but inside the dashed one-dimensional subset. Okay, this is called B boundary. Okay, and this black part, this is a wave, and we just remove this part, and then we calculate the embedding or do the embedding or analyze the data using this subblock. What do we get? Interesting enough, if it is in the 0-1 interval, you suddenly get all eigenfunctions with 0 on the boundary, suddenly. Which is very strange. This looks like its behavior is very much like Dirichlet. And in the disk, you see, so beautiful. All these are eigenfunctions of the Dirichlet boundary, of the Laplace Beltrami operator with the Dirichlet boundary. But why? We still do not know too much. So let me give you some open questions in this direction, which we still cannot solve. So first, numerically, it seems that the clipped LLE gives a Dirichlet boundary condition, but is it really true? We cannot. We haven't have a proof for it. So this is a question. Okay, open one. Second, suppose you can really get Dirichlet Laplacian. Oh, nice, right? Then you can maybe consider, how about if we use it to do the embedding of the manifold with a boundary? Then what do you get? You see, because all the eigenfunctions will have 0 on the boundary, so all the boundary points will be mapped to 0, 0, 0. So this is equivalent to you mud out the boundary and get a new manifold without boundary. The manifold is kind of wrapped up. All the boundary are put together as one point, so it seems to generate something like S2. So will there be any topological interesting stuffs? Well, that will be another question. But LLE itself, it gives you just the manifold itself. But why? How? We still don't know, because when you have boundary, then you get some crazy differential operator. We do not know its behavior, so we cannot even understand why LLE will give you some kind of embedding when there is a manifold. And the embedding in what sense? We don't know. Second, if you go to the very original LLE, you may say, hey, look, how thin. In the very original LLE, the authors suggest to consider W minus I transpose W minus I, which is a symmetrized version and the wrong eigenvalue decomposition. But you just analyze its W minus I part. So what about if you consider the original one? What will happen? Then you can certainly do some calculation. And if you do this calculation, you will see it will converge to something Q bar epsilon, Q epsilon, and F. And the Q bar epsilon is like this guy. Okay, fine. Everything is good. You can do quite a lot. But what you can show is just in the one-dimensional case. In high-dimensional case, you can do the same. But in one-dimensional case, suppose you do not have boundary, you forget about boundary, then you get fourth-order differential operator corrected by third-order P prime. Then you run into fourth-order differential operator. What is it? Okay, and why can it? Will it give you something, some benefit? numerically, it's very interesting if you really pay attention. It is, if not better, at least not worse, right? But we know that if we want to estimate forced order differential operator, we may need a lot of points because you have to do differentiation 4 times. So you need a lot of more points so that you can get a good approximation of forced order differential operator. So technically, you should behave worse. But here, it seems to perform maybe not better, but not worse as well. And if you look at the eigenfunctions, they perform quite well, at least for the first few eigenfunctions. Then why? So 2 questions. Suppose I give you 4 forced order differential operator, then how to use it to achieve manifold linear emission? And to our knowledge, forced order differential operator analysis is kind of, well, not, yeah, it's still an open field. And so we don't know too much. And then, well, how to do the interpretation, we have no idea. There must be something inside that allows us to get the estimation of forced order differential operator in some good way, but that needs to be explored. Furthermore, in the original LLE, people also consider K-nearest algorithm, and you can do exactly the same analysis. And I just showcase you the result. You can also show that, oh, in the end you get a plus Beltrami operator, blah blah blah. Okay. Oh, you get a similar result. So it seems that the original LLE performs better with KNN, which I do not showcase, but at least in some examples, people claim so and so on. But there must be a reason. Why? Because asymptotically, it seems to behave very similar to what we have done in the epsilon bow setup. And one possibility is the density estimation, which needs more analysis. Okay, and there is a paper about the diffusion maps using KNN, published in about 2020, which has some partial interpretation, but well, there's a lot to explore in this direction. Okay, so I think that is the final slide about augmented vectors near the boundary, which I have shown you before. What you can see is the augmented vector near the boundary is very, very strong and has some specific pointy direction. But away from the boundary, it is kind of relatively small. So this can actually be used to detect boundary, but it will be not we will focus on in this lecture. Maybe in the future, when it is more mature, we will discuss it. So I think that is it for this lecture. Yeah.